Operation of protection systems depends very much upon what is happening in the power system and our ability to measure these conditions. In this tape, we're going to look at ways to help us monitor and understand what's going on in the system. First, we'll look at features and limitations of the first link in the chain, that is, Cts and Vts. We already know from earlier tapes that sensing information is provided to the protection system by coupling the relay to the load circuit through instrument transformers. Current transformers, Cts, and voltage transformers, Vts, step down the power system current and voltage to safe working levels. This provides significant protection to the relay and also to personnel working on the protection equipment. Low voltage and current also permit the relay equipment to be made small and precise. Typically, the relay will work at, say, 5 amps and 120 volts. The instrument transformers are a critical component of the protection system, and consequently, they must be accurate. It's vital that the voltage and current provided to the relay from the transformers be a true representation of the current flowing or voltage level at a specific location. As we'll find out later, this may not always be the case. Instrument transformers conform to the normal relationships between primary and secondary windings. For example, let's say the turn ratio on this current transformer is 1 to 50. If the primary current is 250 amps, what is the value of secondary current? This is equal to the turn ratio, 1 over 50, times the primary current. That is, 250 divided by 50 equals 5 amps. Both the primary and secondary of a CT are built with relatively few turns of heavy wire, and this results in low impedance. This is desirable because if the impedance were high, it would create a high voltage drop in the load circuit. This CT is called the window type. It is also known as the straight-through or donut type CT. The primary winding is the power conductor that passes through the window. Since the conductor goes straight through, it is considered to have only one primary turn. The internal winding is permanently assembled on the core to form the secondary. A variation on this is the split core CT. It has a secondary winding permanently assembled on the core, much the same as the window type. The split core CT opens up, allowing a power conductor or bus to be placed through the middle of it. Another type of CT is this toroidal type, which is often used at lower voltages. The magnetic core is in the form of a ring. The 3 phase conductors pass through the ring, and any out of balance due to ground fault produces flux in the core. The secondary winding feeds current to a ground fault relay. And here is a bar type CT. This type is equipped with both primary and secondary windings, with the primary having again only one turn, while the secondary has many more. CTs are normally marked with their rating on the nameplate. For example, a 400 to 5 amp rating speaks for itself. 400 amps flowing through the primary will produce 5 amps in the secondary. This would be used where the anticipated maximum load current is just below 400 amps. But you will often see something like this, 600/300/5 rating. This rating indicates that the secondary of the CT has a center tap. The outer tap will provide twice as many turns, so the ratio will be twice as high, that is 600 amps to 5 amps. Often a large number of taps are provided so that the CT can be used for various applications.
Note that in all cases, the rating of the secondary is 5 amps.
For the relay, the most important aspect of the CT is its accuracy in reflecting the current at fault levels, which may be at least 10 times normal load current.
Now, CT performance. In an ideal CT, we just saw that the ratio of primary to secondary current is the inverse of the turns ratio. However, the core must be magnetized, and this is done by using a small amount of the current supplied to the primary. This additional primary current results in distortion of the current that is induced in the secondary. Because of this, two errors occur. One, a ratio error, and two, a phase angle error. To compensate, correction factors are calculated and provided by the manufacturer. This diagram shows a typical ratio correction factor curve for a current transformer. You can see that the correction factor is very small indeed for normal loads, about 0.3%, but the error increases significantly as primary current increases above rated value. And here is the correction factor for phase angle. The correction is shown in minutes of a degree. You can see that the error is very small, less than 1 degree.
The phase angle error is important in revenue metering, but it really has little effect on relay performance. In fact, for relay operation, we're really concerned that accuracy is good for much higher values of current, say 10 to 20 times normal full load current.
Standard classification of CTs is based on allowing 10% error for current flow up to 20 times rated value. The main characteristic affecting CT accuracy is that of magnetic saturation. What do we mean by this? Well, it's really a problem of overloading the core. The amount of magnetic flux circulating in the core of the transformer is, of course, proportional to the current passing in the primary. When primary load current increases, then magnetic flux in the CT also increases. But there is a limit to how much flux the core can hold, depending upon physical size. At a certain point, the core becomes saturated, and the flux will no longer increase in proportion to the primary current. Consequently, the secondary current will no longer follow its fixed relationship with the primary. Remember, it is the flux which creates the secondary current. This graph shows a typical saturation curve. Within its operating range, that is up to around 20 times rated current, the secondary current retains close correlation with the primary. But as the primary current increases beyond the knee of the curve, the secondary current is no longer accurate in representing the primary. In other words, the CT becomes non-linear. This particular curve is for a burden of 1 ohm. But look, as the burden is increased to 2 ohms, and here to 4 ohms, distortion starts earlier. At 4 ohms burden, the CT is accurate only to 10 times rated. The term burden is used to indicate load on the secondary of an instrument transformer. The accuracy of the CT at high current flow will be considerably reduced if we add too much burden to the CT secondary. This would occur if we added too many relays and other equipment to the secondary of the same CT. By adding more relays, more current coils are connected in series, so increasing the impedance. The transformer must now produce a larger output voltage so as to force the same current through the higher impedance. To achieve this, more flux is needed, and therefore more exciting current is required from the primary. As a result, distortion increases and accuracy of the transformer is reduced.